Okay, so we put the sixth assignment up. It's kind of like this. First of all, we want you to do this on Signet. So if you don't have your Signet account or you're halfway through, finish it. And if you can't, let us know, and we'll hook you up. Then we're going to take back the wave equation that we did in assignments 2 and 3 in its modularized form. So the first thing we want you to do is make sure that if you didn't modularize it to the point where your I/O was in a separate module, you should do that. And then you should make sure that there's plenty of I/O. We're going to focus on the I/O a little bit in this assignment. So make sure that you write out every time step rather than every few hundred time steps, which was the default before. And then on Signet, to compile and run your programs, you should have some modules loaded. In particular, GCC 481 and binutils. Don't use the default GCC and the default gprof for this. So these two go together. One gives you the compiler, the other gives you gprof. And then compile with -g.spg as explained in the lecture, and you should be getting your profiling information. So you want to figure out where your code spends the most of the time, and then figure out which I/O line is the most expensive, because the next step is for you to change your I/O from the text-based I/O that you had before to binary output, and to do the profiling again and see the difference. Okay? And so we need all your code and a report with the output of the profiling and an explanation of what happened, and your Git log by next week. All right?
Okay, thank you, Ramses. So that's the homework. Let's switch over here. Is this recording? Yep. So today we're going to continue on with the. Here we go. We even got the right aspect ratio this time. So we're going to continue on sort of the third phase of this class. So a week ago we started introduction just to the idea of performance, how to measure it, different tools you can use. Ramses then went into some specifics about serial performance, and there were sort of two phases looking at maximizing your basic serial performance, and he talked about a couple different ideas with cache, file I/O, and some of the things that contribute to that, and how to add performance that way. The other way, and very as sort of a tenet that will be the rest of this course, is okay, I've got a fairly decent serial code, but there's always limitations there. Processors are only so fast, so if I really want more performance, I need to put more processors into the action, or more parallelization of some set. And basically that's the whole way the last few years modern programming has gone, even on down to your local desktop. It used to be just an HPC thing 15 years ago. Now it's not. To get any more performance now, you pretty much have to go parallel, whether that's GPU parallelism, threaded parallelism, or HPC style, multi-node parallelism. So today, this is just an introduction, sort of high levels type of stuff. We're not going to get into any particular paradigm, programming, that type of stuff. This is just general concepts about taking all that serial programming approaches that you've learned and has been beaten into you, and then add on how that translates to do things in parallel. Because now you're not just talking about simple loop structures of one after the other after the other. You either have to think about what work can be done at the same time, and how to not fight with each other, and all the details that come along with that. Okay. So this is, it said, really just introductory. It's meant for why we need parallel programming. I think that's fairly obvious and is not a hard sell nowadays. But limits to it. We're going to talk a bit about supercomputing architectures. If I could spell properly, it's an R they're missing there. But basically how you would target different architectures. I already mentioned a few of them. There's GPUs, there's accelerators, there's on-node programming with threads. Then there's also off-node, and there's different programming paradigms for each of those and how you approach them. And that's what the different parallel programming approaches are. They all kind of center around the same idea, because we're going to do something in parallel, so we needed to divide and conquer at some point in our code. How you approach that can be different whether you have access to the shared memory or the different architecture. And that's what this is all about today. It's just to introduce some of the stuff if you're not familiar with them. So this is just a blanket statement that, why is HPC necessary? I don't think I have to tell most of you guys that. It's a tough sell. It's just big data. We have lots more data. You can't access it from one system. Big science, if you want to scale your problem up, one computer's not going to do it, either for memory or it'll take you 100 years to do something. And you also want to be able to grow into problems that you can't touch before. So this is why we want to scale these applications, either bigger simulations or I just want to do a lot of them. Either way, you're still going to have to do it in parallel. Some are higher than others, but But the thing is, advances in processor clock speeds topped out. We've been stuck around 3 gigahertz for a while. I don't need to get into the technical details of that, but basically there's just, with CMOS technology, there's a limit where the power is just not more efficient to do any more of that. So in order to get more performance, Intel's trying to push that Moore's Law, which is a manufacturing thing, farther and farther. The only way they can really do that is not increase the clock speed serially, but put a lot more into the same die. And what you do a lot more of the same process in the same die, you end up with lots of cores, which is why everything from your cell phone now to your desktop has 8, 12, 16 cores in it. And so that fundamentally applies. Yes, I theoretically have more performance power, but if I want my serial code to run faster, I have to parallelize it. Because otherwise, in a 16-core chip, if I'm running serial, I'm only using 1/16 of the resources available. So I'm kind of forced to do that by the hardware limitations that we're leveraging right now. So this is the whole idea of more cores running concurrently. So even as I said, 2 or more, we have to go parallel. It's not even an HPC thing anymore. It's just a modern computing paradigm. Okay. So why parallel programming? Why would anybody want to bother with it? Well, as I said, the infrastructure requires it at some level. There's a limit we can do serially, and there's a limit to how much memory I can use. On a single machine, I can do it. Nowadays, I can put half a terabyte or a terabyte memory in a server if you want. It's expensive, but I can do it. But what happens if I want to run something that needs 50 terabytes or even bigger? Some of the top machines now have hundreds of terabytes of memory. So you can't do that in a single address space. So you need to divide and conquer it up. So you need to do that as well too. Same with disk if I want to do very large I/O type problems. Anything becomes a bottleneck, right? So if I only have a 1 gig connection from my machine and I want to dump 20 terabytes worth of data, do the math. It's going to take you 4 days to do that. So it's just all these things become bottlenecks at some point. And we want to do the same thing we did before, but we want to do it thousands of times. As I said, we either want to do large parameter studies or an optimization, or we just want to solve a really large problem. So for all of these cases, there's different types of parallel. Some are harder, some are easier, but you're going to have to do some concurrent work. So I mentioned this briefly in Moore's Law. People are like, oh, Moore's Law is still going great, and it is to a point. But as I mentioned all before, they're not doing that by increasing the clock speed. What Moore's Law really is it just says, how much they can manufacture. Every 18 months they can shrink the die size by 12, get more transistors in that node with current CMOS. And that is topping out. Even Intel now, they used to do tick-tock in their architectures. So they do a die shrink, then they do an architecture change and a die shrink. They've been doing that for the last 20-some years. Now they've extended that out to 3 or 4 phases long because they're around 7 nanometers now, and it's getting really, really, really expensive or difficult. You're getting down to atom widths and relativistic effects. So, that's becoming a big issue. So this is just sort of it's the most commonly misquoted one, but basically this is the real thing. It says long-term history it's a manufacturing thing. And so we're still doing that, but even that is people are predicting Moore's Law's death probably for the last 10 years, but it's getting pretty close. But it doesn't increase, I promise you, clock speed. A little bit. It did for a long time. 90s were great. I just waited a year and buy my 100 megahertz machine. I buy a 200 megahertz machine, and it worked great. We kind of grew up like it's great. So a lot of professors got into, I don't need parallel programming. I just wait a year and get a new one. Well, that kind of topped out in the last, sort of in the last 10 years. So we don't get away with that. So we've got a lot more cores now, but they're at a fixed clock speed. So my individual cores are, it's not completely true. You do get a little more out of more modern cores, but that has to do with vectorization, which is a type of parallel anyway. So it's all coming from different levels of parallelism. Okay. Just another interesting plot, just of talking about. It's not just we always talk about transistor performance, but that affects total performance for just iterations like flops, floating point operations, which is important. But as Ramsey's mentioned, memory, and this last one is serial, memory optimization is a huge deal. Same with disk I/O. So if we look at the plot of the green line, that's showing, performance sort of in terms of transistors that's going on. That's great. But if we look at clock speed, it's topped out here, basically died, and then our power here as well, and then our performance clock tops out as well. And if I also plotted our RAM speed, the amount of memory per clock, its plot would be like this. And if I look at disk speed, it would look like almost go down. So that means that, yeah, I can afford to do more calculations, but the cost it is to get that piece of memory, or per unit core, or the amount of disk I/O I can do actually has dropped even more. So even though this is increased, they don't all increase at the same speed. So what does all this mean? All this really, we're just getting to the point, is you don't have a choice. If you want to do this stuff, you kind of have to bite the bullet at some point and either just use a library or get into some sort of parallel programming to be able to solve your larger codes if you want to get speed out of them or do anything just at scale. So all these cores need to do something. So we need to find parts of the code that can be worked independently. That's the thing about parallelism. In serial, we like it in the sense that it's really easy. I say A to B to C. If I need a piece of data later on, I don't have to think about it. I just do things in a nice iterative order. When I want to do something in parallel, just like if I wanted to get 10 guys to do it instead of me, I have to figure out the different pieces and figure out how they can be done at the same time and ideally have as least amount of interaction as possible. Because anytime we have that interaction, that breaks up our concurrency. You have to do it. But the idea is how to minimize that. In some workloads, it's very easy. If you just want to do, image processing or something, and I have 100 images, well, I can run 100 parallel images, and they have nothing to do with each other until the last step. So that's embarrassingly parallel. Or 100 different simulations. That's fine. But if I've got tightly coupled simulations, which kind of come out of like our wave equations and our typical PDE type solutions, where I have to be time accurate within a time step, then I have to figure out ways to break it up either in space or time in those points, right? So this is the ideals. Ideally, order of execution shouldn't matter. You'd like them to be many such parts. But this data dependency, i.e., where you got to communicate, that's what's going to limit your concurrency. But you start to have to think about this when you look at your problem, and you got to think of what do I find the concurrency in this, and what bottlenecks do I see? And some are straightforward, as I said, like our image editing, or you're doing some experiment where you've got a lot of separate pieces and they're separate complete events. Well, great. A parallel for you might be just taking your serial code and running it 20 different times at the same time, and then collating with the data. But if all your 100 steps are one after each other and there's a data dependency, then you've serialized the whole process, right? So best case scenario. This is the, our what we typically refer to as our embarrassingly parallel, where we just have a bunch of parameters we want to run through the same case, and we just run it here 4 times. As you look, there's no dependencies. I can run this one first, or this one, or it doesn't really matter. One could be longer, one could be slower, completely independent. We can run the serial program on each processor at the same time, and then we can get more done. So we have 8 core nodes, you run 8 at a time, great. Didn't cost you any more time, it's just there's more work to be done, right? You've generated 4 times the amount of data. Now, the real world doesn't always work that way, but, for this type of case, let's start with the easiest case first. So we're going to bring up some terminology here, and we've kind of hinted at a little bit before when we talk about parallel performance. These are a way of measuring our parallel performance. So we're going to introduce here the idea of throughput. And throughput, I think you have an intrinsic idea. It's really just how much you can get done in a fixed amount of time. So if we take that simple, embarrassingly parallel workload, it says I'm on my single desktop with 1 processor. And if I run all 4 of them, well, then it's going to take, 4 T times, right? If T1 is our total time it takes for 1. Now, if I do this in parallel all at the same time, well, then it's still only going to take T time, but my throughput has increased 4 times. So this is an important factor, is because a lot of people get focused on their problem in parallel and say, oh, I really need to run this one problem and make it scale to 1,000 cores. But if I have 100 different things to run, it may be more efficient for me to run 10 jobs at a time using only 10 processors, than using all 100 processors for one job, because it may just not be enough work for that. So that's a function of throughput. If you only have one job to run and it's huge, well, you don't have a choice. You need to use all those resources. But commonly, you may be doing some sort of series of parameter studies or something, and so you want to find that sweet spot. And that's where the idea of throughput. It probably will be somewhere between the serial and the very large job, but figuring out how much you want to run and figuring out what's the best balance of the code you either have or you will be changing to. Because sometimes if your job, say your serial job only takes 2 minutes, it doesn't matter how many processors I throw to it. I'm not going to be able to get it down to a second, probably. Or if I am, it's very wasteful. It makes more sense to run 10 of those things all at the same time than to run that one job and serialize them out. And this is the whole idea of throughput. It's just always keep that in the back of their mind. Is at the end of the day, you guys don't really care about, you care about scalability of the code, but really what you care about is the work you're getting done and using the system efficiently. And you're never going to get, anytime we do something in parallel, you're going to lose efficiency. It's always, the serial code is really going to be except maybe a few exceptions, always going to be the fastest one because there's no overhead in it. There's no communication, there's no data breaking up, that type of thing. So if you can get away with that in a reasonable amount of time, it makes more sense for throughput to just run more of those, right? Now, as I said, the true medium is going to be somewhere in the middle of that. But it's just, this is the idea of throughput. So does that make sense? It's a pretty straightforward concept, right? So in scaling, which is the other friend with that, is to figure out how well the job scales. And that really just means, in strong scaling, it says if I have 8 processors and I run it on one processor, it takes, say, 1 minute. Or say it takes 10 minutes or 8 minutes. It's easier. 8 minutes. And then if I ran it on 8 processors, ideally, it would take 1 minute because then I would be perfectly scaled because I would be running 8 times faster, right? This idea of strong scaling is referring to taking the exact same problem and just dividing it up into smaller pieces, right? Now you can see where that limitation would come because eventually as you break it up into smaller and smaller pieces, there's going to be less and less work to be done. But if the workloads are big enough, ideally this is where you should try to target, right? So for an embarrassingly parallel job, this is true. There's zero overhead. If it takes 1 minute for each of those jobs and I run, 8 of them, I can get them all done 8 times faster than if I ran them one after each other, right? So whenever we talk about parallel performance, one of the first things where you get a new code or anything you want, we will always say, well, how does the code scale? And this is what we're talking about. Whereas if you just plotted it versus, number of processes versus the tasks divided by the time it takes for one or a smaller job, you can see how well the code scales. And this will inform your throughput calculation. Because in a real code, what's going to happen is, somewhere out here, it's going to start to fall over. You're going to get to a point where, okay, for the problem size that I'm working on, scales, 80, 90% really well at, say, 100 nodes, or 100 cores. But at 500 cores, it's down to like 20%. Well, then it's not worth because you're just too small. So it makes more sense. That's your sweet spot. And so that'll inform where you should run because that's where you need to do work on your code because that's where you're falling down. Okay? So the speed up is just the metric or the inverse of that by basically saying the total time divided by the serial component, so how long it would take to just do one of those, by the total time. So speed up in a case of this case where it's 8 times faster, you get a speed up of 8 because you take 8 minutes it takes to do the job all in serial divided by the time it totally takes, and you get a factor of 8. So that's a linear speed up, right? That's your best case scenario. You could also say that's 100% efficient, right? So I'm not losing anything in that calculation. So non-ideal cases, or what we like to call real-world situations, you're going to have to do some communication. This is the cases where I want to take one problem that is coupled. I've got some interdependencies in it, and I needed to figure out a way to break it up and solve it in parallel, and then bring it back together. Now, if you're lucky that the calculations are independent, you're still going to have to do a little bit of pre and post processing. So you'll do some case where I have a pilot, I want to add the numbers to 1 to 1,000, right? So I need to do some partitioning step. Now I know the additions are commutative. I can add those in any order, but I have to break up the data. So if I want to do it on 4 processors, then the first thing I got to do is, okay, you're going to do 1 to 250. You're going to do 251 to 500. So I have to partition it, right? Then in the case this components in here are going to be pretty straightforward. Well, this is the case we're just using integrating some tabulated data, same idea. But then, you're going to different in different regions. Then you're going to have to do a reduction at the end, right? So we're all going to take our sections of the data, right? So these are the 1,000 points or whatever. You're going to do 250 each, right, to load balance and make it all evenly. But then I'm going to have to do some reduction at the end, right? So these individual components in here are nicely data parallel. They're independent. They're fine. But that partition data, some guys got to do their partitioning at the beginning, and some guys got to do a reduction at the end. So we need to gather the data on each processor. These are the parts that are, serial in nature, or could be serial in nature. Yeah.
Mean by reduction?
Well, whatever. Okay, if you're doing an integration, you have to do a sum at the end or something, right? It could be a norm. It could be some sort of collection. You're doing so. In this, if it was a sum, it would just be a global sum at the final ones. And the integration is the same idea, right? It's just you're going to do some sort of collective operation, right? And at the end, we need to bring all that data together. So in this case, it's a sum, just a reduction operation. But just think of it as a sum. It's just okay. So there's some certain, overhead that we refer to it. If I was just doing this in serial, I wouldn't have the top part or the bottom part, because I would just do this guy with this guy under the bottom, with this guy under the bottom, this guy at the end, and it would just be my same loop. I wouldn't have to do that splitting. I would just go from 1 to 1,000, right? In this case, I've got to go to 1 to 250. I've got to do some splitting. So that's just overhead. Now, usually it's relatively small. Ideally, if you're doing a huge, 1 to 10 billion, the cost of this is going to be way dwarf the cost of that little bit of setup work. But you have to be aware of that, right? Same thing at the bottom. If this is, 10 million sums, and this is just a few sums between 4 processors, it should be much smaller. But it still is overhead, right? So this is the serial portion, and there's some overhead to split it up, and then this is the workload in the middle, right? So suppose the non-parallel part time is some serial portion, TS. So there's a fixed serial portion. That's not going to change regardless of how many processors we have stuck in there, right? So if we take that idea and we plug this into Hamel's law, which basically shows how fast we can get with an overhead. So in an embarrassingly parallel, that TS would be 0. And then it just ends up being NT over NT times P. They just cross out and you get 1 over P. So you go back to just our, our theoretical speed up. But in this case, we actually have a serial component. So that's some overhead. And so say if that's just a small amount, you say, oh, it's only 5% serial. Well, let's see what happens if we plug in 5%. So we put the 5% here. We see the curve starts not going to look, even at only on 16 processors, we're already down here to like a 60% efficient at this point. We're wasting 40% of the time, right? Because that 5% is always 5%. It's fixed. So even though as we shrink the other reductions, they're now becoming the same order of that serial time. So all this is really trying to let you know or make you aware is that even if it's a small amount of serial, it doesn't take long for that to become dominant or a big inefficiency in your parallel program, right? It's not to discourage you. Gene Amidal was an IBM guy, and he was trying to show that he was trying to use this to prove that you don't need to do a parallel program. We just want big, faster serial machines because it takes too long, right? But this is more just an awareness that yes, you can solve this problem. It's just you have to be aware of any component that is serial. Now, if it's 0.0001%, you're not going to hit that limit to some place farther out. But you do have to be cognizant that it doesn't take long for any dedicated serial, and also informs your program. Basically, you should avoid, if you can, any things that have to be completely serial. There are other ways to do it. Does that make sense? Yeah, so we can go through an example here. Suppose your code consists of a portion which is serial and a portion that's parallelized. The serial portion takes an hour to run, the parallel portion takes 19 hours to run. So that's our 5% or whatever. Even if you throw an infinite number of processors at the parallel part, if you take the limit of that, right, you can make that very, very short, but then your code will never be faster than an hour because that's the serial part. Right? Even if it's down just to a couple minutes for the parallel part, it's still taking that 1 minute and it's massively dominating everything else. And those processors are sitting there doing nothing otherwise, right? So then in that times, the throughput doesn't make sense to do that, throwing as many as you want, right? So the goal is to structure your program to minimize serial. And this is all the end of the day. You don't want to inherently just say that has to be serial. Usually there's other ways to do that. You always take the big parallel part first, but if you're structurally changing the code, you want to be aware that avoiding these bottlenecks is very important. So scaling efficiency, I mentioned it. It's just a way of, it's just the scale up divided by the larger by the number of processors, right? So it's just another way of saying, instead of saying 1 of 8, or 8 times faster, I can say it's 100% efficient or 60% efficient. It's just another way. So embarrassingly scalable problems would be 100% efficiency. This is the aim. Obviously you're not going to hit 100% for most real codes, but anytime you have that overhead, but anything, it's like 80, 90% is not a bad thing. It's just that's the overhead you're paying when you run your code in parallel. Okay, so now we've kind of introduced some of the vernacular or whatever about the idea of throughput, scaling efficiency, scaling terminology. This is all the type of stuff you'd want to measure, and it's relatively easy. Any of these can be calculated by just literally the time command, right? The time command your job takes for a different number of processors, you can generate all of this stuff. So as we talked about in the performance section, having a handle of what parts of your code do what can help you sort of parallelize the code because you know where to focus on and which parts may be serial or parallel, and you can kind of keep this in the back of your mind to see how well am I doing. Okay, so now we're going to switch gears. We'll talk about how do I target a particular architecture. You're like, well, I don't want to target a particular architecture. I just want to make a code. I like C, I like Fortran, I like Python. I want to just do it in that language and not worry about it. Well, and you can to a point. With HPC, there are very different paradigms, and how you want to end goal run, which problem you want to run, will matter which type of system you're going to run against. So we're going to go over the few very general ones, and I'll talk about specific ones we have at SciNet and sort of emerging ones. And luckily, there's a few general classes, and they do relate, and they're not completely different. But it really does come down to there are limitations if you're going to stick with threading or GPUs. You're not going to be able to solve the biggest problem, or you maybe have to mix both of these programming methods as well. So the first one is clusters. This is what most HPC or supercomputing centers run nowadays. They're just distributed memory machines, i.e. they're just a bunch of nodes. They're just servers, and there's just a lot of them. So we say distributed memory in the sense that if you have code running here and a code running here, they can't see each other's memory. The memory is distributed. They're physically different machines. Your laptop and your laptop connected with Wi-Fi, I can make a cluster, but they can't see each other's memory. So I have to make exceptions for that, right? Whereas if there's two processors in the same box, that's a multi-core machine. They share memory. So the pool of memory, when I type top is 16 gigs, I can load them up and they can see each other's memory without having to communicate. Okay, that's a major difference on the programming models that you can use, because one case you'll always have access to, there's some NUMA issues internally, but you basically have easy access to it, whereas in distributed memory you don't. You actually have to put a mechanism in to send information back and forth. Now, so it's a collection of processors that go together in a multi-core machine. Everything's a multi-core machine now. Limited number of cores. When the machine is very large, this is true, but even now on new machines, we're talking 50 cores or more. This is now just, that's the way it is. You can't buy a processor less than 8 or 10 cores anymore, right? So 2 of those, you're at 20 cores already. So everything is a multi-core machine. And clusters are just more groups of these, but you still have multiple nodes. Accelerators are the other type. These are basically not standard CPUs. So this could be a GPU. So it's dedicated to, they're usually dedicated for some other purpose. These typically have a regular compute node host, like a regular server, with this plugged in, like your GPU. And then you would have to ship the program off into the GPU to do the work. It could be Xeon Phi, which is now a self-hosting accelerator. But it's the idea being a Xeon Phi is a variant of a regular Intel chip, but it's a bunch of lower speed, faster or more performant processors. So they put 72 cores in the chip, but they're a much lower clock speed. And the Blue Gene is sort of similar in that vein as well too. So yeah, the serial code doesn't work very fast, but if I took a throughput of the total machine, it should be better than a bunch of faster. It's trade-offs, sort of thing. And that's effectively what a GPU is too. They use hundreds of, sometimes even thousands of very, very, very lightweight processors in there to divide and conquer, which works great in graphics because, I've got a big 4K screen here. It's easy to take 4,000 lines and everybody take one, right? That's effectively why GPUs were massively parallel machines. And the architecture is set up that way. They don't waste a lot of time on logic. So if your problem can fit into that, you can leverage it a certain way. But the idea being an accelerator is usually there's a slightly different programming model to that, and it's usually hosted on another platform. So you have to be aware of that. Vector machines, there's no real dedicated vector-only machines now. These were your early Cray supercomputers and stuff, where instead of a typical scalar processor where you just go A equals B plus C, and it would just add those up in a loop, it would really work on vectors. So it would say A, B, and C are all vectors of whatever some length, say 128 at a time, and it would do literally one calculation of 128 at a time. So you'd want to break your problem up so that you would be doing these big loops at a time. Now, it's the same cost to do A plus B plus C if it's 1 or 128, so of course you want to have those full vectors. Now this still lives on in what we call scalar processors now. So all your modern processors, Power, Xeon, whatever else, have vector units in them. MMX, SSE, all those terminologies they like to play on those are all vector units, AVX. And some of them are very long, like in the newer processors, that you can do 16 operations in one of those vector units. So what that means, if I want to really use that whole processor most efficiently, if I can fit into those vector units, I can literally do my Saxby or my A plus B on a unit of 16 doubles at the same time for the same cost as if I was just doing it scalar. So even though they're not dedicated vector machines anymore, and just like we don't have clusters of serial nodes anymore, there's pieces of all of these have migrated their way. So being aware of this, what we call vectorization or vector extensions, can be very important, especially if you're doing like matrix type operations, because that can be literally an order of magnitude that you're missing out on if you're not using those. Now a lot of this you don't have to use directly. If you're using, that's why we say you use the math kernel library, MKL. They've written it to use that. You don't have to worry about it. But that's one of the real reasons to do it is they've written the library to do those operations nicely. But this also means, like Ramsey's talked about cache, your alignment in memory really matters, because if you're doing one operation with 10 numbers at a time, you better make sure they're nice and aligned, otherwise the vectorization isn't going to work. And also those vectors have to be independent. If you have a loop from 1 to 100, and it's just in one little loop and you've got a data dependency inside that loop, then it can't vectorize it. Whereas if it's all independent in that loop, it can. So there's little tricks like that type of stuff. Anyway, so most supercomputers are basically a combination of all of these, and it makes the programming messy, but that's where we are. You have to use a little bit of each of these to various degrees. But that's kind of the landscape of what architectures are beyond just a bunch of CPUs. Okay. So so distributed memory clusters, as I said, just existing powerful computers. Of course, your old pets kicking around. That's Ramsey's closet right there, I think. And then you just put them up on the network. They're really just a bunch of computers hooked together. That's what our main GPC is. This is the main system at SciNet. Well, at least for the next 6 months until we pull it out and put a new one in. But the same idea. Anyway, so those first 3 rows, there are 45 of these racks. Each of them has 84 computers in them, and they're all just wired up. But other than that, each individual node is just 8 cores and 16 gigs of memory. It's not that special, but when you take 3,000 of them or 3,800 of them and wire them together with a high-speed network, that's what makes a supercomputer. And that is the definition of supercomputer since basically the last 15 years. Commodity hardware. So, just under 3,800 nodes. They're old now, Intel 8-core nodes, but they still work, but they're not that powerful individually. just over 30,000 cores, about 300 and some teraflops, 16 gigs a node. They are multi-threaded, so you can run 2 threads per core. We can talk about that later. They're running at Linux. The only thing that really makes them different is they run InfiniBand. This is just a high-speed networking. You can use Ethernet. The difference is this has lower latency, so the ping rate is much better, so communications are cheaper. That's all it really comes down to. And then it was, when it started off in the top 500 list, number 16. I think now it's probably even lower than that now. I don't think I've updated. So I think it's on. I haven't updated this. That's actually not even on the list anymore.
That's hertz or gigahertz?
What's that?
Okay.
Yeah, they're really slow. Damn it, that's the problem. That billion factor. Didn't somebody press the turbo button? You guys are too old to probably remember the turbo button. Does anybody here remember the turbo button? There's a few people. So in the earlier computers, they used to clock lock like operations because the chips would work at 488 megahertz. And so some old applications would work too fast. So they had a button that when they got a new one on 286 that you could go from 4 to 8 megahertz by pressing a button. Because they didn't change the processor's speeds at that time. They're not variable. So they literally, in some applications, would lock them. So if you wanted to run an old application, you would press the turbo button off and then run it. It would downclock the machine. So I used to have a game, and if you want to make the guy run really fast, you press turbo and it goes. It's true, because they literally clock locked it, right? Anyway, so a bunch of typos, but whatever. It's an old system. We're going to update this slide next one anyway, right? Anyway, but it's just an example of a classic cluster. There's no accelerators, just CPUs and memory bolted together with a fast, high-speed network. And most of the newer systems are going to be the same thing. Compute Canada's just put in 2 new systems, one at Waterloo, one at Cedar and Graham. The other one's going in at SFU, and they're a variant of this. So each processor is independent, and communication. The only time you have to do anything independently is when you want to communicate back and forth. And that's actually when you program for a system like this, you really are running a bunch of serial codes that are just communicating or organized a certain way. So each processor has its own memory, which is good because now I can generate a lot of memory pretty quickly because I aggregate all this together. However, I have to share it. So if I need a piece of information and all of them have to have it, I have to have duplicate versions of that piece of data. So another reason is to try to be able to split that up. So for this one, this is where MPI programming comes in. It stands for Message Passing Interface. And that's really all it really is. It's not even a program. It's not even a language. It's just a tool. It's a library that allows it to say, okay, you've got a piece of data, you've got a piece of data, I want to send you back and forth. And it allows me to synchronize and do reductions and do those type of things. So when you think MPI, it's for this level of programming. It's just a communication library. Now you can do MPI on the same node, right? That's fine. It'll just share the messages inside. So that's the nice part about it, is that you can use it for all these programs, but it's not maybe as efficient because now I've got certain duplications going on. But it will allow you to scale, and if you want to scale off node, you're basically pretty much forced to use MPI right now. There are other mechanisms, some newer ones, Core and some other stuff, but predominantly 99% of what you're going to get is MPI. Now, a lot of people codes will have MPI and something else to use vectors, to use GPUs, to do whatever else. But basically, if you want to do large, or you want to grow large off one node, you pretty much right now are going to use MPI. It's sort of the de facto standard. Now, in shared memory, you've got a few more options. You can use MPI on this. It's perfectly fine. But there's also some easier ways to do too, because now we share the memory. So there's some organization that needs to go on there. But you can actually break up, this is where the idea of we talked about threads and tasks. You can actually break one processor up into a bunch of individual pieces. So the task can actually be broken into a series of threads. And so then you can operate on each of those threads because they all access the same memory. And you can do this right at the loop level, right? Within a for loop. You can actually literally break up that for loop on 8 processors in groups of 8. And then you can actually break that up, okay? So each core gets assigned a thread of a single program, right? And then you can break that up. Now this is one of the most common ones to do that is OpenMP, and this is what Ramses will talk about in the next 2 classes. And that's basically sort of how to take a serial code, find the loop parallelisms that are inside that, without having to restructure your whole program, hopefully, and exploit this. So that way you get sort of instead of just serial on my 4-core processor, I may be able to get a 4x speed up. It's not going to give you the 1,000 times speed up of using a big cluster, but you get some benefit from that local parallelism. And then there's also this idea of hyperthreading we mentioned, whereas you can overload the number of physical processors you have. Well, if one's waiting to do something, it can slide in the other guy. And that's what hyperthreading really means, is just running more tasks and back scheduling. So our current processors do 4 of that. Some newer ones actually do 2. So they have 8 physical cores. They have 16 virtual ones. So it's just a way of backfilling. Now in scientific codes, there's some debate if this is worth it, because usually you should be 100% busy all the time anyway. But there are cases where you can win out on that, where you can hide communication by swapping in other work. And this is very, very important on things like GPUs, where you literally have to overthread them to get them to work properly. If you want to, there's 100 processor, 100 cores or threads, tasks, whatever you want to call them, in a threads in a GPU, you really want to oversubscribe them quite a bit, because there's a lot of overhead moving things in and out of the GPU. So yeah, we talked about this a little bit when we showed top. Here's the idea. If we looked at our node running our OpenMP code, we see it running just under 800%. That's the single process ID, one number, right? But then if we turn we see it, if we run the MPI version, we get 8 different ones, right? So it could be doing exactly the same sort of thing. This is just programmed in MPI, and they run as complete separate programs, independent tasks, whereas those share the same chunk of memory, and it's programmed with OpenMP. So it just shows up a little differently. So this is the idea of processes, which are independent tasks, versus threads. Threads are lighter than tasks. And just to be clear, this MPI does not preclude you from doing this. Quite the opposite. Hybrid programming, it's usually referred to, means take an MPI code and OpenMP internally of it. Use sort of MPI on the large sections back and forth, but then you thread locally. And this is actually very important on a large system. So I have 50 cores on one box. If I have to run 50 MPI tasks, I'm spending a lot of time communicating off node. Whereas if I could run less tasks, say 5 with 10 threads each, I can reduce a lot of that communication overhead. But it does require you now to have to program things 2 levels of parallelism. And that, unfortunately, is very common in a lot of newer systems to squeeze out all the performance. You may have to do things a couple levels deep. Memory and communication stuff, I mentioned this a little bit. Gigabit Ethernet is the most pervasive. This is similar to what your Wi-Fi, just regular TCP/IP stuff. Bandwidth is pretty good nowadays on Ethernet. You can do 10 gig, you can do 100 gig Ethernet, so pretty good bandwidth. But the latency is kind of crappy. And why we care about latency? Latency is the time it takes between to get a message from here to there. For all you gamers out there, it's a ping rate, right? How long, that sample time, if you're before you get a piece of information back. And that's very, very important when you're doing tightly coupled communication programs. If I'm sending an MPI message, it's small. I don't want to have to wait. If I have to wait a long time between those, I'm wasting a lot of cycles. My processors are in the order of, not hertz, but gigahertz, right? So we're talking nanoseconds. So if I have to wait, 10,000 nanoseconds to get a piece of information, I've wasted a lot of time. So to get around that, they have higher speed networks, which are lower overhead, a little more expensive, not as much now, but just structured differently. And they're better in bandwidth, but where they really win out is they're much, much faster on latency, or much better latency. So they cut out a lot of the middleman. They make the software stack better, they make all this other stuff. And this is why we say on our system, when you compile with our MPI, make sure you use one of our MPI libraries using the InfiniBand, because that's where the big win's going to come out, right? Especially as you scale up to a large size. The message rates, the amount of messages you can send, and the speed at which you'll get will actually show up in your scaling. So some code that might scale, okay, on Ethernet, or only scales to a certain size, may scale very, very well on InfiniBand, right? Now NUMA is non-uniform memory architecture, and that's on a node, and that's what controls multiple processors or multiple cores accessing the same chunk of memory. Because there's got to be some controls. You never see that, but if processor 1 is going to try to get memory block 7 over here, there has to be some coordination going on, and that's actually handled under the hood by this NUMA architecture. But it's very fast. Right, so we're down into the reasonable nanoseconds, or cache latency type, a little slower than cache, but still. And then the bandwidth is pretty high. So this is just sort of levels of hierarchy, right? and sort of the costs associated with it. So here it's pretty good. You can get away with most stuff with the loop level. Here you got to have sort of large, blocks of your program, like a pretty significant amount of data. And then out here you better have really, really big blocks of data if you're just running over Ethernet, right? And communication is always the slowest part. All of these are much slower than the calculation. Now, so the name of the game in parallel programming is minimize communication. Do as little as possible, right? Design your code to do you do it when you have to, but only when you have to. Because communication in this case is not work done. It's overhead, right? The iterations, the calculations, those are what you want to get done. The communication is not really, unless you're doing a communications study or something, it's not really you're not getting effective work done with that. It's just overhead. So we want to minimize it. So hybrid architectures, we've already introduced those. That's the idea of just, every modern system has now multiple cores and a chunk of memory, and it may be more efficient to, use less MPI. So instead of using 4 times 24 separate MPI tasks, we use 6 MPI tasks with 4 threads each, right? So that's what I said. The idea being is we reduce the communication overhead because I now can work on bigger chunks and then thread them out locally, as opposed to dividing it into 24 little chunks. I just keep it into 6 bigger chunks. Now, there's always a balance in there of now I have to program things MPI and OpenMP, and some people always don't know which way you start, and there are different algorithms and different schools of thought on that. But this is becoming even more and more important. As I said, on the newer systems, like our systems are only 8 cores. There's still a certain amount of overhead, but on the newer systems they just bought at SFU, I think they're all 32 and 36 core systems, right? And newer systems that we'll be looking at are sort of more in the range of 48 cores, right? So you're spending, it's a 50-to-1 difference, Now, I know you may not want to run 48 and 1, 48 threads in one, and Ramses will get into why that's not great, but having some balance of that. And we see this on the Blue Gene too, which has 16. So this type of hybrid programming is very much in vogue to get most of the performance and reduce that communication overhead. So hybrid architectures with accelerators just take this to the next level. They usually call this heterogeneous programming because now I've got programming that's not the same on every node. I could have a GPU in each of these nodes, plus a processor, plus memory. Now I got 3 levels of programming because I got to program for the GPU, program for the processors, and do my MPI communication if I want to go across node, right? But these GPUs are in some problems are very worth it because they have a lot more compute capacity per, unit work or whatever, unit dollar or unit flop or whatever you want, right? There's a lot more theoretical capacity in them. But you kind of have to stand on your head a little bit to get there. It's not for the faint of heart. You can't just, your OpenMP and your MPI are bolt-ons to your standard programming languages. You just take Fortran, you take your C code, you put some paragmas or some language constructs in there. The GPU program isn't. You literally have to restructure your program and use CUDA or OpenCL, another language, to do that in there. You don't get them by just recompiling. So it's more work, but it definitely it may be worth it. Okay? So that's the downside, is you need some sort of specialized programming language. Now, OpenMP is starting to get into offloads in the newer versions so that you can use variants of OpenMP to do that, but it's coming. It's not there yet. So right now there is so this is the idea of using multi-level programming, right? And as I said, that's not what us as programmers want to see. I don't want to do 3 different things 3 different ways. So unfortunately, that's what the hardware is right now. And some of the stuff like CUDA is specific to NVIDIA only GPUs. So this space is still very much in flux because nobody's really won out yet. So all we can really do is, adapt to the thing. But what is consistent is the idea of all those parallel constructs apply for all of those. Yeah, the syntax is different and maybe how I exactly approach it. But this idea of reduced communication, to be able to do independent tasks and you need looking for concurrency is exactly the same, independent of how you're actually applying it, right? Those are higher level concepts that apply to all of these. Okay? So, the programming approach depends on the type of problem you have. So embarrassingly parallel applications, you can just script with GNU Parallel. GNU Parallel is just a tool that allows you to, and I'll talk about it a bit, and I think one of the next lectures. Do I have it in here? Maybe I do. can't remember sure. Anyway, but it's a tool that allows you to take a bunch of serial operations and kind of like meta schedule them. Shared memory, that's OpenMP threads or POSIX threads. We're not talking about that, but it's another type of doing lower level threads. That's what your operating system uses. Distributed memory, you're probably going to use MPI. There are newer PGAS, which stands for Partition Global Array Address Space, so UPC, Co-Array, Fortran, but they're sort of up and coming. MPI is by far the dominant one. Same with GPUs. CUDA is NVIDIA-specific stuff. There is OpenACC and OpenCL, which are other variants that can do that as well. And then hybrid combinations, some combination of all of these. The ones we're going to talk about specifically are two most common, OpenMP and MPI. And then we do give other courses and some of this other material as well too that we can talk about. The other thing to think about is what type of problem you're really working on. Is it data bound or computational bound? Now, most of the time we think about parallel, we usually think about compute bound. Oh, it's taken me 10 hours for this job to go, and if I broke it up, I can actually run it faster because it's the amount of iterations I'm taking. This is you focus on parallel process threads. How do I add more heavy lifting to this? Do I need more processors? Do I need more threads? How do I break it up? They have very different computations to do, but you want to, in this case, you want to bring the data to the computation. So you split it up or you keep it up for that type of workload. Now, in data bound, this requires data parallelism. So here the operation is a large data set, and you want to partition it in a way that you can access it and keep it local, right? The data set is often an array, partitioned to tasks to separated partitions. And in this case, you want to bring the computation to the data. As I said, if the data is the largest limitation, then you want to bring that. So not message passing the whole thing around makes a lot more sense, and just everybody pulls its own piece. So as I said, if we take that image processing case, one processor doesn't load up and grab all the images and then send it around to everyone. No, every processor just go and grab their own piece of data and work on that, right? It makes more sense. So it's just, this is once again, there's sort of thinking about data versus compute bound, where you're seeding from, what you're going, where your application targets that. And you can shift from one to the other pretty quickly too, because if you might start off with some toy problem that's in 1D, when you're like, oh, it's all compute GAN, I don't really care about my initialization, I don't care about my serial steps. But suddenly I start to look at my real science problem, and it's 3D with all this other stuff, which is some big, large seed data set that, maybe now I've shifted the level of problem. So knowing, along the line where you're going can inform your approaches that you want to use. And as I said, you start developing, I built this great OpenMP code, works great, but now I want to solve my real problem. I'm like, I'm out of memory because this machine only has, whatever X number of gigabytes of memory. Well, maybe I should have focused on MPI because I need to run a really large problem. So this is just questions you have to ask yourself, and there's no real only one answer. This is just another way of thinking about parallelism, just more terminology for the type stuff. When we talk about fine-grained parallelism, this is loop parallelism. This is usually your threaded, your shared memory model type stuff, because you're literally looking at down to the for loop or the do loop level where you're just going to break up that loop, right? That's why it's called loop parallelism. But in that case, you're going to have access to shared memory. So these are smaller individual tasks, smaller workloads, and the data is transferred only, frequently inside that loop. So you only want to do that usually at the shared memory model. Now in coarse-grained, what we usually refer to MPI as task-based parallelism, where I literally want to carve out a chunk of my problem and give it enough workload that it can work independently. So this is the divide and conquer. Data communication is infrequent because we don't want to do it because it's expensive. And so this usually fits your distributed memory model. Now you may have some mix of both of those. Typically you might, because you do have loops inside there, but you also need to be able to break it up into a series of pieces, right? So if something's too fine-grained, you spend all your time in overhead. If it's too coarse-grained, then you can run into load imbalance. If I have only very large chunks, and I can only break my problem into 4 pieces or 12 pieces or something, and I run with 11 processors, and now I'm going to have load imbalance. I'm not going to be able to keep my processors busy evenly because I only have big pieces of data to work on. So this is just something to think about when you're setting up your problem. And this really much depends on what you're doing too, and how effective these are really depend. If you're on a GPU, this becomes much more important because or coarse grain doesn't really work on a GPU because you have to throw 500 or 1,000 threads at it, right? But if you're just doing pure MPI, you can get away with, oh, I can run on 12 or 14 cores. That's perfectly fine, right? So that's architecture specific as well. So summary, it's just you have to do some parallel programming to get full performance at some level. Avoid serial stuff. I mean, your codes are all initially serial because it's just how we program. And most program languages, there's no native. There's very few, if there is any one. Even I would argue that there are none native parallel fully implementations right now. We're still using serial codes. So you're still going to have serial portions, but the idea being is to not, the codes may be serial, but you're going to think of the data access and what you're doing as not serial operations, right? You avoid those cases to minimize them so you don't avoid those sort of Amidal type problems. There's many different types of hardware available. They're all basically clusters of some sort, just multiple in an HPC sense. But I mean, you can actually do all three of those programming on your laptop. You can program with your GPU, you got multiple cores, and you can do your MPI all within your desktop and test all of those as a reference. The only difference when you go on the cluster is now you have multiple nodes to do this and maybe a faster interconnect, but it's the same thing. And the programming approach, people don't like to hear this. They say, well, what should I do? I should open MP or MPI? I don't know. Choose your poison. Now, both of them probably is the answer. And so we're going to talk about that in the next few days to make sure you at least have an introduction to the most common forms of that. Okay. So I went through that pretty quickly, but this is meant to be just a high-level sort of welcome to the wonderful world of parallel programming, and we'll confuse you further with all the ugliness of the syntax and details that'll come out in the next, 4 or 5 lectures. Is there any questions about any of this general stuff, or I try not to use too much terminology and get bogged down in the weeds here a little bit? But okay. Okay, so I think that's good, and see you guys on Thursday or next Tuesday.